Hi there. So what I'd like to talk about is two identities, two matrix identities that involve Kronecker product and also Khatri-Rao product. So let me just write it down. So if I have actually I will just clean this page actually. If I have A, B, and C three matrices. So let's say this is n by n, and then n by k, and then k by l, let's say. And if I look at the vectorization of this matrix, what I mean by vectorization of matrix is, let's say if I have a matrix W, let's say this W is composed of columns W1, W2, and so on. So let's say I have n columns here. So it's again, let's say this matrix is n by n. So then the vectorization of this W will be just stacking all this vector into one very long column vector, basically W1, W2, and so on up to Wn. So therefore, instead of for size n by n, as a matrix n by n, it becomes a column vectors of length n by n. So this is n by n there. So, and the vectorization of this product of this matrix A times B times C will be equal to C transpose Kronecker product with A multiplied by vectorization of B. And also, if this turns out this matrix in the middle is diagonal, so let's say if I have matrix, if I have a vectorization of A times D times C, let me erase this here to get some more space. Let's say this is n by n. Let's say this is n by n. And this is n by l, so this is a square diagonal matrix. Then I will have this is equal to C. Let's see, I think it's still C transpose Khatri-Rao product with A times the diagonal of D. So this diagonal of D is just take the diagonal elements and put it as a column vectors. So for example, if I have D here is equal to D1 up to Dn here, so this is a diagonal matrix, the rest is 0, then diagonal D is just a column vector D1 up to Dn. So okay, we are going to show these two identity, and I guess maybe I should give a quick review what this Kronecker product and also Khatri-Rao product means. So if I have, let's say I have A times B a Kronecker product, so let's say this is a matrix of n by n, and this is let's say k by l. So this Kronecker product will give me a matrix of size m times k by m by n times l, and basically it's just tiling this B matrix into just tiling the B matrix and weighted by each element of A. So more precisely, I will have something take the let's say this A here, the elements of A is let's say this element of A here is A11 and up to AM1 and so on, A1n up to AMN, let's say. Then this A Kronecker product with B will be A11B and A21B and so on up to AM1B, and I have this here A1NB and so on and so forth up to A and B here. And this is the Kronecker product I didn't write it down. Kronecker product. I think it's a Kronecker product. And this is the Kronecker product. If for the Khatri-Rao product, if I A this circle dot B, basically this is very similar to the Kronecker product, but you see for the Kronecker product, I'm expanding the matrix in both directions here. But for the Khatri-Rao product, the cat, I think it's spelled like that. Khatri-Rao product, I will only expand in the vertical direction, so I only increase the number of rows, but I fix the number of columns. In more precisely, I will have, let's say, this matrix A again is n by n here, and for B here I need to make sure the number of columns is the same, as you will see why I need that. So I will say, so therefore let's say this is the dimension k by n, and let's say more precisely my B is something like B1 column, B2 column, so on, have n columns denoted by this B1 up to Bn. And A, let's say I have the same same curve denoted by, have the same elements here, A1 up to AMN here. So then my Khatri-Rao product will be equal to something like A11 times B1 and A21 times B1, and so on and so forth, up to AM1 B1. And for the second column, I have A12 B2, and so on and so forth. I have AM2 B2, and the last column I have something like A1N Bn, and so on and so forth to AMN Bn. So then now if you look at that, then you see that the number of rows here will be this matrix will have a dimension n by n. So there will be number of no n by m, I'm sorry, n by k, right? I have n by k rows here, and number of columns here is still n. So let's say the Khatri-Rao product here will be n times k by n. And by the way, as you see later on, I will use one very simple property here. Is if I try to figure out what's the ij elements of this, let's say the Kronecker product here, the ij element, basically, I'm sorry, I guess here, I want to make a slight changes here because of the indexing. So instead of I use this index starting from 1 up to n and m1 up to basically 1 up to m and 1 up to n, something like that. As you will see, it's more convenient if I assume this A here will have the index from starting from 0. So what I mean is I will, instead of 1 1 here, maybe I just use a different color to override that. So I have start from 0 0, and then this is 1 0 and so on. And here instead we go to up to m minus 1 and 0. So I'm just changing the index. So it's changing from MATLAB to C and Python, that kind of indexing. So it's more convenient for me, as you will see afterward, because if I take indexing like that, then basically the ij one, if I look at the ij element of this matrix here, I will have basically if I take I as, or maybe I put it this way, think of if I have some of have a small n a m n in the middle, and with some b here. So this is because I'm doing this tiling of this B matrix here inside this conical border, weighted by this AMN. So I should for a index MN where M is like between M minus 1 and 0, and N is between like M minus 1 and 0. So I will have like a term here like AMN times B. And let's say like in here, like if I look at like which elements, like of course I will have an element that will have like B, let's see, MN is okay, BKL, let's say MNKL. So that would be like a BKL element inside this B matrix here, where K is inside 0 and K minus 1, and L is between 0 and L minus 1. And I want to see like where is this element. This is I would say like this element will be the ij element there, right? And basically that I will be equal to, it's quite easy to see, should be equal to M times wait a sec, yeah, M times K plus small k, right? Let's see, I think it's right, yeah. M times N, M times K plus small k, and J is like N times L plus small l. And for that index, I should have that element A, M, N, and B, K, L. So A, M, and B, K, L, basically. There is a product, really. The inside this big matrix, what I'm saying is like, okay, let me just summarize here. Inside this big matrix, like A, X, B here, each of the terms is something like that, right? If you expand that, basically each of the terms is like some element of A multiplied by some elements in B, and in particular, the element, the Mn element of A multiplied with the K element of B here should fall inside the matrix in the ij index, where the I is a Mk plus K, and J is NL plus L, something like that. So it's very easy to see, right? Because you just do a simple counting here. So I have like if I have A Mn here, so should be that basically A Mn and BKL. If I consider the element A Mn times BKL, it should fall inside this A Mn times B, this tile here, or this submatrix here, and this should be how many rows below that would be like I should have like M minus 1. Oh, okay, maybe I'm missing M minus 1. Let's see. M is okay, I think. So I start with index 0. That's why I want to start with index 0. Yeah, that make it a little bit easier. So I start with index 0. Then it will be like M times K here, right? So that's MK row here, and that's the number of element here is going down, will be like plus K basically, right? Actually, I need to plus it's okay, I don't need to plus 1. If I assume the ij index is also like starting 0 or something like that, that's fine. Here I just use a Python C notation. Please forgive me for that. Like I know that like in math probably it's more natural to use the starting the one index, but here we make it a little bit cleaner if I use this C and also like Python convention here. So, but yeah, as I said, like then it's very easy to verify like this way. So the ij, the element with like AMN times BKL is basically the MK plus K and NL plus L element of this A X times B matrix, and a Kronecker product with B matrix. And by the exactly same token, I will have the term like mn and b, let's see, bkn. Right, this term here is inside this kind of Khatri-Rao product here, and this term inside this Khatri-Rao product is actually for in the is the m k plus k row, because it's essentially the same thing for the Kronecker product. When you expand it along the vertical direction, like both Khatri-Rao product and the Kronecker product is expanding exactly the same way. But for the column, if we extend it horizontally, it's easy. It's basically, if we don't have an expansion, so we say just end there. So basically, I will have something like that. Okay, this is maybe I just write down this final equation that we were going to use in the proof. So this is for Khatri-Rao product, and again for the Kronecker product here, I have actually something like that. And k plus k and l plus small l. Yeah. Okay, before I continue with the proof, let's first look at some application of these identities here. So first of all, let's consider the problem of trying to approximate matrix from kind of like a large matrix into a lower rank matrix. More precisely, let's say I have some H here, and let's say the size is like m plus l, and I'm looking for if I can approximate that into like some a times b times c, where in this case my a here, so it's precisely like that, but like my a here is a kind of a tall matrix here, my b is kind of small, and my c is like a fat matrix here. So something like this is like I have a and I can say like write the a decompose, put the a's represent as like by its columns, say let's say maybe a1 up to a n here, and c also I let me just represent c by its rows here. So I have a here, this is my c will be like c1, this is the row c1 up to ck, so, and this is like c here, and so then of course when I write this, this is essentially a low rank approximation of this matrix H here. And also like if we kind of like expand this by the columns of A and the rows of C, this essentially will give me something like or something like I can, this product here is essentially equal to the sum of weighted sum of some of the rank 1 matrices that is created by multiplying like column of A by rows of C. So more precisely, I have like B, let's say B and K here, let's say B and K multiplied by A and C small k here. Actually, I use index from 1 again, but it's okay. When I go to the proof, I will use index from 0 instead. So, and this is a sum of n and k here, something like that. And you see like this is basically some rank 1 matrices, right? Rank 1 matrix, and this is just weighted sum of that. So, and here we are assuming that this rank 1 matrix the basis, so we want to look at like how H can be decomposed as like weighted sum of this rank 1 matrix basis, and we of course we are assuming A and C are fixed, and we're trying to minimize B here. So then for this kind of problem, like essentially say something like minimize B such that like I want H and it's close to like A times B times C, right? And with the Frobenius norm here, the Frobenius norm is basically just a sum of square of all the elements in the matrix. And with that, I can change this by vectorizing like both H and also A, B, C. So this problem is identical to if I vectorize it to H and vectorize this to A, B, C here. So then this will become just a vector. I want to look at the norm of the vector. Some square of the elements will be just a second norm here. So what I mean is, for example, the original matrix maybe is I say is W1, W2, W3, W4 like that, right? So the Frobenius norm will be W1 square, W2 square, and all this sum together. When I vectorize that, I will just have like from one vector here, W1, W2, W3, W4, and then the norm of that will just square of that, like regular kind of like L2 norm for vectors. And now we can use our identity, how it becomes very useful. We have vectorized of A, B, C is actually equal to C transpose conical product of A multiplied by a vectorize of B, right? And we have this like that. So now if we look at this problem now, it's just a regular like this like minimum solving this least square error problem for a for a system of equations, something like. So we say something like Ax time is close to B, something like this kind of like problem, and the solution for that is well known. This is actually just the solution would be just a best estimate for x would be simply the pseudo inverse of A multiplied by B. So therefore, like given that the immediate solution for the B will be just I will have the best B hat, and the vectorized version of that will be just equal to C transpose conical product with A, and then pseudo inverse times vectorized of H. And there's an application for the first identity here, and by the same token we can do the same kind of we can also use the second identity, but just for a slightly different setup. So when we have, instead of like B is a entire kind of arbitrary matrix here, if it turns out that I only allow diagonal matrix, that is this is a diagonal matrix D, so and this diagonal matrix is square matrix, and then then the dimension for C will become n by L, so there should be n rows there. Now then in this case, we want to find D such that best approximate H given A and C. And this is essentially this kind of like very similar to like SVD here, and this one, if you expand that, will be just like as before. Will be I have like sum over n, but now I will have like just dn here, where like let's say D is equal to a diagonal matrix D1 up to dn, and the rest is just 0, and dn times A n cn, something like that. So note that the difference from the previous setup is that like previously I have like intermixing of like columns of A with each different rows of C, and here like we are basically only the ith column of A is mixed with the ith row of C here, and so and then we with this with this one, if we try to solve that, it's essentially the same thing as before. We want to minimize, in this case, minimize D such that the vectorize of H minus vectorize of A, D, C, the second norm is as small as possible. Again, we can use that equation here. Then this is actually equal to vectorize of A, let me erase this, all this here first. Is equal to C transpose Khatri-Rao product A times the diagonal of D. Okay. So again, therefore the minimum, the optimum D, the diagonal value of the optimum D will be just equal to this C transpose Khatri-Rao product A pseudo inverse times the vectorized version of H. Actually, I want H here. This is H here, something like that. So okay, this is some applications for this identity. Now we're trying to show these identities are correct. So first of all, we want to check the dimension is right first, right? So I have like A times B times C. The dimension is like M times L, right? Let's consider first this first identity here. A times B times C have the dimension is M times L, so I vectorize that. It basically is a column vector with a M times L, length M times L. And for this guy here, C transpose have dimension L times K here, and A has dimension M by N here. So therefore, like the dimension of this conical product here will be L by M, by K by N. And also like the B have dimension M by K, so we vectorize that. I will have a column vector of like K by M by 1 here. Right. So okay, therefore like at least this like product makes sense, right? So my dimension here matches, and after the product, like I will have like a L by M column vector. So indeed, like okay, the dimension matches. Dimensions match. So then the next thing, like what we are going to do is say, let's say we look at the I value of that on the right hand side and also the left hand side of the vector, and just want to show they are the same. So let me start with the right hand side. Let's say I have CT A vectorized B, right? So let me consider let me consider the ith element here, and this I will have, so this product here I will have sum over, let's say J, and C transpose times A here, IJ vectorized of B, BJ here, and now I consider the J, and let's see if I am doing, this is very confusing. I don't want to. This is okay, like for this A and B, okay. Please ignore this here. I don't want the J to be this guy. I'm thinking like what J I should pick. So first of all, okay, the matrix. Okay, before I continue, I probably want to specify where the J is from. So J is from 0. So here, like in the proof, as I said, like I want to use the Python and C convention, like with indexes start with 0. So and the length of the vector is a K by M, right? So it's a sum over K by M minus 1 up to K by M minus 1 here. So let me instead of summing like j from 0 to k minus n minus 1, I can sum over j with two sum. One is a sum from k equal to 0 to k minus 1, and the second one is like n from 0 to n minus 1 here. And I have like j is equal to let's see, k by n. I want j to be, let me just write here, I want j equal to k let's see, it should be n actually. I think it should be n by k plus small k. Let's see if it makes sense. So if I pick a j like that. So anyway, I will cover, okay, when n equals to 0, k equal to 0, then I'll cover like j equal to 0, right? So when n is equal to the maximum equal to n minus 1 here, and k is equal to k minus 1 here, so I will have n minus 1 k plus k minus 1 here. That reach the maximum value k minus n, k times n minus 1. And you can easily verify that like this is basically cover like all the possible value of j from 0 to k minus n minus 1. And of course, like the number of j here is equal to k times n, and this here like I cover k of them, this cover n of them. So so also like this kind of like a sanity check that it should match well. So then I would say I would pick j as this instead. So vectorize j as like n times k plus k instead, like c transpose a I. This is like n times k plus small k here. But now I like to think about like what's this like. I have B is a matrix like have a dimension n by k, right? N by k. And so then the vectorized version, so I have like vectorized version of B taking the n times k plus small k element is essentially equal to the nth row here, not exactly the nth row because I have my first index start from 0 here. So you can think of it as the n plus 1 row, but anyway, the index is at n here, and with this number of sorry, not nth row, nth column here, the n plus 1 column here, but like the column with nth index here, and like inside that column, I look at the k element there, or more simply, what I'm pulling out is actually the b and bk n element, right? Yes. Oh, wait a sec. I think this is supposed to n by k. This is n here. Okay, I made a mistake here. Apparently, I don't want this. Instead, I want j equal to k times n plus small n. So, okay, that should work out fine. K plus n big N plus small n. So it's like k plus big N plus small n here. So now this should be good. So I'm taking I should take the column with the k index here, and in that column with k index I take out the nth element, and that element is basically just equal to b and k there. So in summary, like this thing here is actually just give me B small n k. Now I want to do something similarly for the I. So I here, I want to pick I. Let me what do I want to pick? I want to pick I from let's see. I have C transpose, have the dimension is L. So I think I should pick I something like L small m plus small l. Let's see, does it make sense? Let's see. I pick I from here, like ml plus l. So, and what I mean is that of course I can be originally like I'm looking for I that should take value say from 0 up to the maximum of this thing here is m times l minus 1, right? Now if I pick small m and small l, and I allow small m and small l, let me remove this here, where I allow small m to be from 0 to big M minus 1 and small l from 0 to big L minus 1 here. So again, if I look for all this M and L, and then actually I will have like I is from like 0 to M times L minus 1. So exactly what I want. So let me repeat. Originally, like what I want to make sure is that like I look at each of the element in this vectors. I want to show the right hand side is the same as left hand side here, and the number of elements there is like m times l here. So the index coming from like 0 to m times l minus 1, and so instead I go for like each I from 0 to m times l minus 1. I go a little bit indirect. I look at a small m from 0 to m minus 1 and small l from 0 to l minus 1, and I take I from like m times l plus m times big L plus small l, and if I do that, essentially I have I will cover the entire range here 0 to m times big L minus 1. Okay, so if I do that, so I have I equal to this instead. So so I will rewrite this as a k equal to 0, k minus 1, and 0, m minus 1, c times a, and then here, so therefore I have m times l plus small l, and k times m plus small n, and times a b and k basically. Or actually I have already b and k here. Multiplied by b and k. And actually I think we are already done, because if you look at that, we have earlier that if we look at a conical product here, if this is like my dimension here is like L by m, and this is like k by n here. So then the conical product of this and the nl plus l element, the kn plus n element, is essentially just a C transpose, the let's see, yeah, C transpose the mk element, C transpose not the mk element, m and oh yes, that's right, m and k element, right? So that's a little bit confusing looking here and here, I'm sorry, but essentially this one, you match this guy here, small m is still the same, but like my big K become like big L, and my small k is become small l, something like that. So my here, like my small n here becomes like small k, okay? So I should have like m and n here, so therefore I should have like mmk here. I see transfer mmk here, and also like a with so the latter part here is like with index k and l, so it's k and l here, and this basically this and this here, so it's l and n, right? So okay, this element is actually turns out to be is equal to this, m now times like b n k, right? And if I look at C transpose, the mk element is equal to C the km element, right? So because I transpose, I flip that. So I have mk element cmk, and can reorder that. So I should have like aln times bnk m times ckm. So let me just remove that here. ckm. So this is sum over like k m n. That's of course it's just like a times b times c, right? The l m element of a times b times c, and lm element, if I look at the vectorized version of that, is actually is equal to vectorized a b c. The l m big L plus small l element, and this of course is just equal to I, right? So therefore, like I exactly have that. So I have this guy, the ith element is equal to this guy here, and of course I is this, but like it doesn't matter because I can change m and l to cover all the possible range of I, so it works well. So for the other one is like essentially this very similar proof here. Let's see if I can just change a few notation and complete that. So I have, again, I start from the right hand side here. I have a diagonal value instead, and now I also look at the ith element. Oh, again, like maybe even before that I should check the dimension is correct. So a times d times c, the dimension is m times l here, so therefore this column vector should be like m times l times 1 here, and for C transpose time a here is l times the dimension here is a l by m times wait, I need to be careful because I cannot copy from above because I am using different first of all, C transpose is a L by M, so it's still N here, L here, and A is M by N, so L times M, yeah, that's right, and by N basically, yeah, that's right. The dimension of this Khatri-Rao product here, and diagonal D, of course, the dimension is just n by 1, so I multiply that. Indeed, like the dimension matches. Again, we do the same thing here. So we look at I is the yeah, actually it's right. I can pick the same I here. It's ml plus l. Again, I pick value from 0 to m with from 0 to big M minus 1 and l from 0 to big L minus 1. Then as I vary this m times m and l, I will cover the entire range of I here. That's from 0 to m times L minus 1. And so maybe I just change a couple of things here. And this is like multiplied by d. So, but of course, my j doesn't change like from 0 to k times n minus 1, but just to n minus 1 here. So because the length of d, the diagonal length of the diagonal of d is only n values there. And then so we essentially do the same thing here, right? So I can have j here. Actually, I don't think. Let me just here. I guess we are already done, kind of. So let me just erase some of this here, and we say I is equal to this guy, right? I is equal to this guy. So I have like C transpose A. I is ML plus small l, J diagonal. Maybe I don't use J here. Let me use small n here. This is okay. Small n index. So I don't have a J here. So just not to confuse with the previous case here. So it's a small n to n minus 1 here, diagonal d n. So I just repeat the previous line here, just change my I with like ml plus small l. But then if I look at this one here, I already know that like from another kind of simple identity we got earlier. So this is actually equal to the, let's see, C transpose M and A L and is equal to C transpose M times A L N and times the diagonal of Dn, or maybe just Dn here. From n equal to 0 to n minus 1 here. Let's see. Of course, like this then is just equal to, then this is just equal to dn times c times ALN times CNM, right? Actually, it's easier to put the dn in the middle. To see it, ALN dn, sum of n equal to Cn minus 1. Then actually it's already clear this is precisely the product here, like A times D times C. And we are looking at what the LM element of that, the LM element of A times D times C, and the LM element of that, if I look at the factorize of this A, D, C, the LM element of that, of course, is just M times big L plus small l here. Again, this is just what we have the I earlier. So therefore, again, this guy here is equal to this guy for every I that is given by this M times L plus small l here. So again, we have this second identity is shown. So okay, I guess that's it for today. Okay, thank you for listening.